So I am Sandipan and I will be conducting this session. So we have 4 talks lined up in this session, which encompasses topics from topics related to ethics and trust in natural language processing to differential geometry and graph neural networks. So our first speaker is Dr. Vivek Raghava. Welcome, Dr. Raghavan. Dr. Raghavan is the Chief Product Manager and a biometric architect at the Unique Identification Authority of India. He has been responsible for the design, implementation, and scale out of the technology platform for Aadhaar, the world's largest identity program, mostly as a volunteer. He joined the Aadhaar project just when the first Aadhaar was issued and was there when the billionth Aadhaar was generated. So he has an MS and PhD degree in electrical and computer engineering from Carnegie Mellon University and a BTech from IIT Delhi. In the past 3 years, Dr. Raghavan has been exploring the use of AI in many public and governance domains. He is driving many AI initiatives at Aadhaar in the areas of biometrics and document validation. So Dr. Raghavan has been responsible for guiding the development of ML models at GSTN and NPCI as Chief AI Evangelist at the EK-STEP Foundation. Dr. Raghavan has been advising the National Language Translation Mission to develop open datasets and open models for language AI technologies for Indian languages. So he also serves as the member of the AI Committee of the Supreme Court of India. He has been a long-term volunteer with ISPIRT Foundation, where he is a contributor to the DEPA. Over to you, Dr. Raghavan.
Thank you, Sandipan. And I will share my screen. I just want to make sure that, can everybody see my screen?
Yes, we can see your screen.
Okay. So first, thank you for inviting me to speak at this event. I have been spent probably the last 10 years of my life working on different kind of public good projects within India. And in the last 3 to 4 years, I have been involved in various kinds of AI projects, and part of it partly in the government and partly as a public good as outside the government. So therefore, I wanted to actually talk about 3 interesting attempts, and to tell the truth, they are still attempts to actually figure out interesting ways of creating data sets that can have societal benefit. And I want to just see that the various kinds of approaches that we are taking for this, and I hopefully as a result of talking here, maybe there may be certain collaborations that may come out of that. So I just want to at least give an idea of what kind of things are happening in this nature. So here I'm going to talk about actually 3 different kinds of works and 3 different examples. And really, I'm going to talk about specific examples of dataset creations that we are attempting to work in the public good space, in the societal space in India. The first one is actually is to leverage DAPA, and DAPA is actually I suppose India's answer to GDPR. It is something that is actually going through the parliament and other things. So therefore, it is leverage DAPA to create data sets to enable models in things like flow-based lending. So therefore, that's a first area, and how we are actually putting together, trying to create some kinds of a techno-legal framework to actually enable the creation of certain kinds of data sets for this thing. The second area which I want to talk about is actually related to the National Language Translation Mission, where basically we want to create an open data ecosystem for Indian languages, and at least I want to share how far we have come on this. And all of these are actually at the very early stage. And the third one is actually an effort which I'm involved in, which is basically creation of community-based data sets and benchmarks in the legal and justice domain. So, so therefore, I think hopefully this will be a coherent presentation with actually 3 very, very diverse things there. But I want to actually at least leave with the flavor of the kinds of things, of the kinds of data sets that we think are possible to kind of create in India and specifically in the Indian context. Okay. So then first, I'm going to talk about moving to the first first area is basically I wanted to talk about the data empowerment and protection architecture. This is actually a techno-legal framework which for sharing of data between different entities. And at its core level, this data framework, and this is actually something which is already been notified by the Niti Aayog in India. For those who are in India, well, notified by the Niti Aayog in India, and is also going to be part of the Privacy and Data Protection Bill that is currently in Parliament. But I think the core thing is some of the key things that we think that it is not only that obviously the right the privacy of people's data is a fundamental right, but also the right of people to actually share their data for a relevant purpose to actually obtain certain services is also enshrined in this bill. So it is a kind of so therefore DAPA is actually a resident consent based framework where the consent flow is separated from the data flow, and the sharing of data is by definition purpose and time limited. So the data is, when it shares from one entity to another, the data is always shared in a manner that the purpose and the time of it is limited. In addition to that, the framework kind of ensures the accountability and authenticity of the data shared because it is signed by the person who's the data provider, right? So and this data framework is already kind of live in at least in one domain, that is in the fintech domain. There is what is known as the account aggregator system, and that is actually uses this data framework to basically allow people to share financial data for purposes of getting loans and those kinds of things. Now, the interesting thing is that we are actually so therefore DAPA is already there, and I think that but one of the extensions to DAPA that we are working is to actually extend data to create what is known as a confidential clean room, to actually allow very interesting places in the flow to actually do both model inferencing and model training in a kind of a secure manner. So therefore it is, if you look at it at a very high level, what really a confidential clean room is actually it's a policy driven data sandbox. So there is a policy which guides what can exfiltrate from the sandbox. And it is a data sandbox which actually leverages some of the more recent, confidential computing kind of advances, so to say. So maybe before I move to the next slide, I want to say the key point is that there are three kinds of entities in DAPA. The first kind of are the people who are the financial information providers. These are the people who have certain financial information. The second entity in the place is the financial information users, who are people who can basically use this data to provide some service to the data. And then there is basically the data owner is the user, okay? And that is the person who is actually, that's the person who is the owner of the data. And the data flows from one entity to another purely on the basis on the consent, explicit consent, purpose and time limited consent of the owner of the data, which is the resident. Now moving to the, how does this actually, now we talked a little bit about DAPA, and I want to talk about how something like this could be, for example, used to, for example, provide so one of the things that in the account aggregator framework is to actually create an ecosystem. So therefore, when there is a person and the person wants to actually, for example, ask for a loan, then the loan information is actually so ask for a loan. What can happen is that the resident can consent to share their information with not just one provider, but basically a marketplace of providers of loans. But when this case is, it is done but this data is not shared with the consumer directly, but is actually shared to a clean room. And what this clean room actually would do, the clean room has actually got a data usage policy. And the data usage policy means that only those things that can be exfiltrated from, as for any use case, you have to have basically using a policy markup language, you have a concept of basically what is the data, what data can exfiltrate from the room. So then while the data is provided by the provider to the consumers, it is provided only within the context of the clean room. And what happens is that the person who wants to actually maybe potentially offer a loan to the consumer would actually move their models into the clean room, where it would basically, and then the model inferencing would take place in the clean room. And what would come out will be only that data which is consistent with the policy of the, which is consistent with the, which is consistent with the data usage policy. So it's basically, if you look at it, it's created, you've actually created a sandbox of data. And so therefore that allows you to share the data more freely with a number of people, because you know that the data is being accessed only within the sandbox. And the sandbox is such that and I won't get into the details of those things, but the intent is this sandbox are kind of, this is kind of you can basically remotely attest to the fact that the sandbox is actually, is in a legitimate state. So therefore that the remote attestability is one of the key points that you can actually do as part of this ecosystem. Going into a little bit more kind of a detail as to what does this sandbox look like. There are basically some of these kinds of, they start with the hardware root of trust, that all of these kind of sandbox are built on a hardware root of trust. And there is basically what this boundary is what is known as a confidential virtual machine, where there are a number of different containers which may exist. But the most important thing that these do is that there is basically a sidecar which is created, which traps everything that comes in and passes it through the policy engine before sending it to the application container. The application container itself is a black box, which may be doing various things, but it can't communicate with the outside world except through this except through this sidecar container, which is basically governed by the policy engine. And that's really the essential method by which you can technically guarantee. Obviously, there are legal guarantees that the data is used only for the purpose, but we want to extend this to be able to actually have technical guarantees that the data is only being used for the purpose for which it was intended, and that because that is coded into the policy. Now, moving to this same kind of flow actually is something that also can be used to actually train models in a manner by which train models in a within a confidential clean room. In this case, of course, when in an inferencing flow, you're looking at one piece of data, but here you're actually in the clean room contains already anonymized data, right? This is the data even before coming in is anonymized, but it's only anonymized. So therefore, and then what happens is, instead of and this anonymized data is made accessible to an entity which wants to train a model. Okay, and the entity wants to train the model, but the training again takes place within this confidential clean room. And the intent is that when you do that, you actually create a model. And the intent of when you create that model, the question is that you then can run various differential privacy tests on the model created, so that you can prove that whatever has been created here is not exposing any of the data of the individuals which was used to train the model. Then the resultant differentially private model can actually be used. So why is this important? Because right now, if you look at it in the world, it's a kind of right now a new player can't come into any ecosystem because they have no access to the data, and that is really the situation where and so therefore you really have no. But what this allows is that multiple people can actually have access to the larger set of data and train more effective models, moving basically the entire ecosystem forward. And that's really the power here, that basically you can have access to much larger, much larger quantities of data to train models in a manner that is actually privacy preserving, and it is, and of course, then it basically makes the ecosystem more vibrant and get more people into this. So all of these things, so these are all, so the work till here, I've been working with the iSpirit Foundation, and I've been a volunteer with the iSpirit Foundation for many years. So therefore, these are some, and then some of these account aggregator, this DEPA thing in the fintech space. It is something that we are working with a number of early kind of. I'm having trouble hearing you. So we are working with a number of what do you call that? Number of companies to actually pilot this and see how this works. And of course, the reason why this is important is this is a pattern which actually can be moved to many different domains. Even though this starting in the fintech domain, it is a pattern which can actually be useful in a number of domains. And that's really the intent to say that the techno-legal framework we have in India has opportunity to actually allow this kind of access to data, which I'm not aware is available anywhere else in the world. Now, so so we talked about basically, in the context of confidential clean rooms and data, we talked about the finance. Now, the next one, we're actually moving to the National Language Translation Mission. And, I think this is a mission which was actually announced this year. And it's announced, it's not yet even actually been launched. So it's a little bit of a preview of what is happening in this. But the intent is to obviously, India being a multilingual society, to actually allow, break down the language barriers and provide content and services to citizens in their own language, both in the form of speech and text. That is the intent of the mission. But I think what's more interesting is actually how the goal is that how we want to achieve this mission. And I'm an advisor to the mission, so therefore it's the goal is to really create an ecosystem of players, including the government, the industry, academia, research groups, startups, and individuals, really, to actually create this ecosystem and actually work on looking at various methods to actually create large open source. And here we are about open source data sets by bringing in all contributions, both institutional and citizen ways, to basically create a shared repository that everybody can use for innovation. And then, of course, once you build this kind of base, and we'll talk a little bit about the architecture, the intent is to actually allow the ecosystem, not just while certainly the government and public entities will build certain kinds of reference products and services, but the intent is actually to leverage these data sets and these models and to actually build various kinds of applications. Therefore, that's the architecture of the thing itself. And I think that one of the key things, and what I'm going to talk, there's lots of things, layers here, but I think the core here is actually this data model and benchmarking repository, which I have in the middle layer over here, which is actually kind of which is being served by this unified language contribution API ULCA, which we'll talk about in more detail on collecting different kinds of data sets and models for Indian language kind of applications. And if you look at it, on top of that, we want to build, and we have already built, crowdsourcing apps, benchmarking tools, open APIs, catalogs for discovery of models and data sets, leaderboards, and these kinds of things. So therefore, this is actually the foundation layer. And on top of that, of course, our intent is to build various kinds of reference applications, but primarily also allow the marketplace to innovate and create and make sure that all the services that we provide are not just in English or a few Indian languages, but is available widely across different languages in there. And at the top level, of course, we have the campaigns and innovation challenges and things like that. So maybe I'll just, this is, how are we for time? I think I will basically have a video here. It's about 6 or 7, I'll at least start the video, maybe we'll stop it a little bit, 6 or 7 minutes long. And then I'll encourage people to go to the ULCA website, which is basically talks about this, what this effort is. So I'm going to play this video.
Hello everyone, welcome to ULCA. ULCA, which stands for Universal Language Contribution API, developed by MIT, is a standard API and open scalable data platform for datasets, models, and its benchmarking for the Indian languages. ULCA will help researchers develop language AI technologies including machine translation, automatic speech recognition, and optical character recognition in all 22 Indian languages. ULCA aims to become the premier repository for the Indian language resources. All the APIs used in ULCA are documented as open APIs using Swagger. There are 3 main components of ULCA, namely datasets, models, and its benchmarking. To train AI models, large amount of data are required. ULCA has a collection of such large datasets that have been collected over a period of time. ULCA supports summation of the following type of datasets: parallel corpus, which are basically parallel sentence in 2 different languages with the same meaning; ASR or TTS datasets, which contain audio to its respective text mapping; ASR unlabeled, which are audio file snippets without the transcripts; OCR datasets, which are images to its respective text mapping. ULCA will expand to other dataset types such as POS, NER, NLU, and NLG, etc. The dataset contain records belonging to various domains such as news, education, finance, healthcare, sports, and many more. These records are collected through various methods such as machine translated with post-editing, auto-alignment algorithm, crowdsourcing, etc. ULCA also contains a repository of language AI models in Indian languages. These models have typically been trained using the datasets we talked about earlier. A trained language AI model performs some specific tasks such as machine translation, which means automatic translation of text from one language to other language; automatic speech recognition, meaning automatic transcription of audio data in Indian languages; optical character recognition, meaning automatic detection of text in Indian languages from images. Already, 59 models in machine translation, ASR, and OCR have been submitted to ULCA. Over time, it is expected that researchers will submit better tuned models for the various language AI tasks. Let's demonstrate how some of these models work. Let's start with translation. Maybe we can search for English Telugu and select, say, Anuvad English Telugu V1 model. Let's try this model. So we have the output for the model. Now let's try out something in ASR. Let's try a Tamil ASR Vacancy model. Let me click here and do try me. Okay, let me try speaking a fairly lengthy sentence here. பிரதமரின் ஏழைகளுக்கான உணவு பாதுகாப்பு திட்டம் தீபாவளி வரை நீடிக்கப்பட்டு மாதந்தோறும் 80 கோடி மக்களுக்கு இலவச உணவு தானியங்கள் வழங்கப்பட உள்ளது. Cool. Let's convert. Check the output. Okay.
भारत की विभिन्न भाषाएं कम से कम 4000 साल पहले उत्पन्न हुई। भारत से निर्मित हुई लिखने की अलग अलग विधियां जो ईसा मसीह से भी 500 वर्ष पुरानी हैं। भारत में हर 50 किलोमीटर के बाद भाषा बदलती देखी जा सकती है। Let's convert it. converted text is now shown in the output window.
Let's try something from the OCR model. For OCR, let's consider an image text. We will
So,
share detailed information in further videos.
So I'm going to stop here. So, but in the end, I think that let's go back to. How do I get back to the? So the intent. One second. How do I? Yeah, so therefore, I think that you can go through the thing, and there is also the Ulka Live website, so you can actually go and see what is there. This is actually in a pre-release form, but it is available and at this link, and you can actually go and see live and try out the various benchmarks. There are a number of, so yeah, the important part which I actually removed there is extensive benchmarking. So therefore, every what do you call that model can actually be benchmarked against all the published benchmarks that are available for that class of So I mean, just to go and show you maybe just a quick view on how benchmarks looks like, and I'm showing it live here. So if you see here, like for example, let me just put something in Hindi. So yeah, so therefore this is a WAT this thing. So therefore we have various different WAT benchmark for 2020 for English Hindi translation. And so basically, and the interesting thing is anybody can actually as long as you have an endpoint, you can actually self-publish your own results on this leaderboard. So therefore that's so I'd encourage people to go, if you're interested in this thing at all, to go in there and look at these things as far as. So let's now move on to and then of course, the other interesting thing which is there as part of the national mission, which I won't talk about, is actually there's a crowdsourcing app where people can actually help contribute to their own language by correcting or contributing either their voice or transcription capabilities or translation capabilities. So therefore, and all of this actually, the intent of this is to actually make this to involve school children, involve kind of other people and language enthusiasts, various people, to actually help collect larger data sets to be made available in Indian languages. So that's the Bhashadan crowdsourcing website is actually, that's the purpose of that. I think this the intent of this is to actually there is a roadmap for this, and I won't go into too much of the details, but the intent is to actually, we've already published the API, we've created the repository, the benchmarking system, and had various kinds of data collection tools. And the intent is to actually use this foundation to actually achieve kind of English equivalence in terms of language AI capabilities, NLP capabilities in all Indian languages. That's the intent of this mission, and would look forward to having people help and join us in this journey. Now I'll switch tracks to the next topic, which is actually kind of to create open source software and data sets, to create AI-powered solutions to advance access to justice. And this is completely a community-driven activity known as Open Nyay. And the intent is to actually, develop benchmarks that are relevant. So create data sets and create benchmarks, much in the style of, style of Squad or something like that, to actually create meaningful benchmarks in the Indian legal domain and allow researchers to come and to try their hands at these benchmarks and to see whether we can actually solve problems that we think are important in the Indian legal Indian legal space. And of course, the goal is, if we make good enough benchmarks, and I'm not saying that we have so far, then we can actually push the ML community to work on NLP tasks that actually benefit the Indian legal system. There are a number of lawyers who are part of our team, and of course, there's a number of different tasks, and we have actually published a white paper of the various kinds of benchmarks we hope to create as part of this this entire effort. I think one of the early benchmarks that we are working on is basically trying to create structure out of court judgments that are there. So therefore, basically to identify the rhetorical rules that are there as part of any individual judgment, and to kind of classify the entire judgment into one of these one or more of these categories, and actually try and that's one of the benchmarks that we are working on. This has obviously, while itself it's an intermediate output, it has a number of implications, including better summarization and better understanding of similarities between cases. There are many applications for this class of things. So we were one of the early areas to actually create this. Of course, the rhetorical rules can be used for summary creation, judgment prediction, charge identification, precedent recommendation, and a number of different things. That's one of the benchmarks that we've created. This benchmark is actually live, so you can actually go and look at this data set and try and look at understand and try to see contribute and see what there is a baseline result which is also there, and it is live, so you can actually go and submit something and see what you can do with it. Now, this is obviously one of the unique things about this was actually created by the data sets itself were created by law students and law experts, and they actually created and hand annotated and made some of these data sets. Of course, there's a bunch of tooling that is involved around that, which actually helps tooling which allowed to create some of these annotation tools and things like that. And I think those are independently useful. If someone wants to use those things, that also makes sense. And finally, of course, we are hopeful that this benchmark will see some wide interest and people will try to use it. So I think the white paper about benchmarks is also given as a link here. So I think at this stage I'll probably come to an end of my talk, and maybe we'll try to answer a few questions at this stage. Thank you.
Okay, thank you, Professor Raghavan. We have enough time for questions. So if you have any question, you could write it down to the QA section in Zoom, or the panelists, if you have any question, you can just unmute yourself and ask questions as well.
So I have a question regarding so this is Anirban. Hi.
Hi, Anirban.
So I had a question. I want to, understand the first part of the talk, the one where you're talking about the clean room.
Yes.
So, technically, implementing the idea is nice, but implementing that technically, it does not look that obvious. That's I guess an obvious statement I'm saying, because what you are then seeing is that you have to the models that will be deployed have to either certify themselves to be differentially private. Basically, in some way, you have to certify that the models are not leaking any. You have to bound that information leakage. And how do you think we can do that? Is there a technical problem that we have to solve before this is deployed?
So, if you're talking specifically of differentially private, whether the models are differentially private or not, there has been a lot of recent work in the last 1 year, where there are some of these standard methods which in a black box manner, you can actually understand you can actually have some interesting bounds with respect to the differential privacy of the models themselves. I'd be glad to share some of those papers offline, but I think there has been some very interesting work in the last year or so in this area as far as the differential privacy of the models themselves is concerned. Yeah. Just
to clarify, so we're not talking about developing differentially private algorithms. What we are saying is that anybody comes and I have to certify that this is a differentially private algorithm.
Correct. That's correct. So obviously, if you look at pretty much most of the deep learning algorithms. Now, obviously, there is some kind of accuracy penalty for being differentially private, but most algorithms have the differentially private versions of those algorithms are there. But we are not even saying that you need to train that way. You could train the model in any way, and then you can actually just pass it through the a differential privacy test to see that indeed that it is not violating differential, that it is meeting certain standards of differential privacy.
So we have a question from the audience. So the question is, normally centralized design approach is prone to single point of failure. Are these frameworks designed in distributed way?
No. Yeah. So there is nothing fundamental in this saying that this needs to be central at all. It can actually be. It can definitely be a distributed framework. That is not. Obviously, that is not something that the framework itself defines whether it is central or it is distributed. I'm assuming that you're talking about the first part of this talk. I don't think the second and third part that is that relevant. But in the first part of the talk, yes, these things. There is, in fact. There are many parts. There is obviously the concept of a logical clean room. A logical clean room actually even consists of many different entities, which may contain different parts of that clean room, and they may all be. And we've also worked out that scheme where actually it is the clean room itself is distributed across, and the clean room is running multiple entities. Actually run the clean room. The whole concept of this this confidential computing is coming up from the cloud vendors. And that's the interesting part, that that the cloud vendors are now saying that they want to be able to guarantee that not even their people, right, are basically able to access anything, that even though you're running on the cloud, that the privileged users within there. So that's actually the starting point, and they wanted to have this hardware root of trust to achieve this. Now, we were actually trying to extend this mechanism really, and by the way, a number of people, and I think that it is again something which is a new thing coming out. We believe that both all three, whether we are talking about AWS and Google and Microsoft, are all kind of going to come up with these kinds of confidential computing environments. But we are trying to extend that to to come with a mechanism that people can share data with each other safely in a confidential manner. That's the intent of what we want to do. This is obviously early work in the sense that there's a large amount of work to be done. But I think that thinking in this way and combining it with some of the legal empowerment that are there in India actually makes it very interesting and may allow people to share data in different ways.
So there is another question. So how can industry professionals like data scientists, ML scientists contribute to any of these different missions in their spare time or as volunteers? So I think that if you look at the first item, that is actually it's actually a completely volunteer group. So all of us are volunteers, and there are people and we are all volunteers under the iSpirit umbrella. Okay, so therefore, and that is the iSpirit as actually one of the volunteer organizations, which you may have not been aware that many of the kind of digital public goods in the country, like for example, they were responsible in defining the UPI interface. They were responsible for in the National Digital Health Mission. There are a number of different API, and of course, most of the people like me also have an Aadhaar kind of a background. But the intent is that is, so therefore, it's a purely volunteer organization. And so if you want to come and join these kinds of things, we do have these meetings and we keep discussing where some of these things go. And if you want to contribute in that area, that's certainly something that we can do. Of course, yes, as far as the National Language Mission is concerned, we are hoping that this whole data being open and being available to everybody is one way that we expect that and anybody also can contribute the data. Now, this is something which is the mission itself has not been launched yet, but we expect it to be fully open and available. This available for people to
because we believe that, as I mean, and I'd say this as an Indian, I feel that we should, we should own our languages, and we should, and that's really the intent of actually involving large numbers of people in whatever capacity they have in aiding their own languages. And the third one is also a volunteer effort. So please reach out to me. I'm glad to, I'll be glad to kind of connect and see whether there's an makes sense.
Okay, we have time for maybe one last question, if there is any. Okay, so it doesn't seem like it. So, so someone has asked you to share your email ID. So I guess.
Yeah. Yeah. So I think I'll share my email ID. How should I just put it over here, or what do I want to do? What's the right way?
So I think there's another question. Any application to blockchain?
Any application to blockchain? I mean, I think that I don't know directly. I mean, I think directly I don't. I mean, I think there is obviously kind of indirect ways in which these techniques used can also be used. When we talk about the very first one, things can be there can be things that can because to actually do those kinds of things, you need to have registries and some of those things. And when you have those registries, you can actually make those registries kind of public on a blockchain kind of an environment. But so therefore, there are certainly certain parts of those architectures where blockchains could be useful, but directly not related, I would say.
Yeah. So I have another small question, which is that we have a lot of uncertainty in our hardware systems.
Yes.
Like the cloud sometimes doesn't work. Most of the time, institute emails are unreliable. They begin to drop mails. So many of us shift to Gmail. So this sort of, these are small things, but this in one way builds up a little bit of it's loss of faith among people about getting the data, accessing the data. So this is
no, I think that your skepticism is well founded. I think the intent is that access to data, whenever we have said it, we have actually not even actually should be available for people has always been a challenge. And I think that in the end, we as ordinary citizens have to actually kind of try and see that how we can make sure that when we create some of these things, and a lot of the time I spend is actually to say that we advocate that this data be available and at all times. And I think it's something that, if we are going to look at some of these things, we have to make that as almost something that we consider as our first priority to making this data available.
Thank you.
Okay, so I guess that brings us to the end of the first talk. So let's thank speaker Dr. Raghavan once more. So our next speaker is Professor Michael Bronstein. So let me just quickly introduce you. You already know him probably. So he's a professor at Imperial College London, where he holds the chair in machine learning and pattern recognition and head of graph learning research at Twitter. Dr. Bronstein received his PhD from the Technion in 2007. He has held visiting appointments at Stanford, MIT, and Harvard, and has also been affiliated with 3 institutes of advanced study, TUM as a Rudolph Diesel Fellow, at Harvard as a Radcliffe Fellow, and at Princeton as a short-time scholar. So Professor Bronstein is the recipient of Royal Society Wolfson Research Merit Award, Royal Academy of Engineering Silver Medal, 5 ERC grants, 2 Google Faculty Research Awards, 2 Amazon AWS ML Research Awards, among others. So he's a member of the Academia Europa EA fellow of IEEE, IAPR, BCS, and Ellis ACM Distinguished Speaker, and World Economic Forum Young Scientist. So in addition to his academic career, Professor Bronstein is a serial entrepreneur and founder of multiple startup companies, which have been acquired by Intel and Twitter, among others. So Professor Bronstein, over to you.
Thank you very much. Thank you for this introduction and for the invitation to speak here. So I hope you can see and hear me well. So I would like to talk today about maybe somewhat different view on graph neural networks. As you probably know, they have become very popular in many fields, including natural language processing and processing of social network data and chemistry and structural biology, just to mention a few. And I think it's interesting to think, well, to me at least, when I think of about explainable or interpretable AI, right, or machine learning, I think one of the probably first steps towards this is to try to put them on solid mathematical foundations. And this is what I will try to do here, at least to present some links that are probably less known or maybe slightly more surprising in this community. So let me start maybe with a broad quote or claim. So first quote is from Hermann Weyl, a mathematician. He was writing that symmetry, as wide or as narrow you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And the second quote is from Philip Anderson, a Nobel-winning physicist. He said it even more briefly. It is only slightly overstating to say that physics is the study of symmetry. So symmetry is really fundamental. And we can see that it was a driving force that unified geometry in the end of the 19th century, the famous Erlangen program of Felix Klein. And similar ideas can be used and reapplied to in the field of machine learning to try to unify the zoo of different architectures for different use cases and for different data. So this is what we try to do in our book on geometric deep learning, try to derive some of these popular architectures from first principles. And if some of you might have seen my keynote talk at ICLR this year, I will not repeat it. I will just briefly recap it here. And you can see some more details about this Erlangen program of machine learning on the website geometricdeeplearning.com. So if you think of supervised machine learning as a kind of black box that interpolates the function that maps you from the input to the output, one thing that you can do in order to cope with phenomena that complicate this problem in high dimension, namely the curse of dimensionality, is to try to leverage geometric structure of the data. And that's what we call the geometric deep learning blueprint. And essentially it consists of looking at three different objects. So one is the domain on which the data is defined, and it's convenient to think of images. So images are not just multidimensional vectors, they come from a two-dimensional grid. So they live on some discrete two-dimensional domain. So they are signals on this domain. And then when we, for example, want to classify images, we apply a function to signals on this domain. So we have the domain omega, we have signals defined on it, and we have some function defined on these signals. So the structure of the domain can be modeled by the symmetry group, for example, the group of translations in the case of images. It acts on signals on the domain through the group representation. Again, in this example, it would be the shift operator. And then we can impose the structure of the group through some prior that we call invariance or equivariance on the functions that are defined on this signal. And again, just to give you a very clear and very familiar example, convolutional neural networks are a very famous instance of this blueprint. So we have the translation group, the shift operator, and the shift equivariance, which is manifested through convolution or convolutional layers in convolutional neural networks. Another interesting example are graph neural networks, where the symmetry structure is the permutation group, coming from the fact that we don't have a canonical order of the nodes in the graph, and then it acts on the node feature vectors through the permutation matrix, and then permutation equivariant functions are, for example, a message passing mechanism that is commonly used in graph neural networks. So you can see that this is also an instance of the same blueprint. Now, these ideas can be applied to different domains. We can apply them to grids, for example, right? We can apply them to graphs, as I mentioned. We can apply them to meshes. So these techniques are popular in computer graphics. And one thing that you notice that all these domains do have some continuous analogy, right? So in the case of a grid, for example, we can think of it as a discretization of the plane. When we have meshes, we can think of them as discretization of two-dimensional surfaces or manifolds. We don't have this continuous analogy for graphs. And to me, personally, this is very disturbing. So we would like to answer this question: what would be a continuous model for learning on graphs? Now, if we look at the way that graph neural networks are typically implemented, it is a form of local aggregation. So I look at a node in the graph, I look at its neighbors, I take the feature vectors of the neighbors, and I put them together. So together they form what is technically called a multiset, because features can appear more than once. So it's a multiset or a bag. Together with the feature vector of the node itself, we need to aggregate them. And I remind you that because we don't have a canonical ordering of the neighbors, this aggregation must be permutation invariant. So we must apply some symmetric function to these inputs. And this is how typically graph neural networks are structured. So we have some permutation invariant aggregator, we have some learnable function that applies to it, and we have some set of weights that can either depend only on the structure of the graph, or they can also depend on the features themselves. And it can be shown that the sum, the obviously far more mostly used aggregation function, is sufficiently expressive. We'll talk about it in a second. So we can use learnable coefficients. This is the attentional flavor of graph neural networks, or we can use a general nonlinear function. In this case, we get the message passing graph neural networks. And we can also augment it with positional encoding. So the attentional flavor is very commonly used in transformers, in natural language processing applications, where we do actually have an order of the tokens that come in a sequence. So usually this order is captured by positional encoding that attaches some descriptor to every node in this graph. Now, when we apply this kind of aggregation at every node of the graph, we get a permutation equivariant function. So if I change the order of the input nodes, the output will be changed in exactly the same way. And it appears that the choice of the aggregator is very important, and it was shown that message passing graph neural networks, where the aggregator is injective, are at most equivalent to the Weisfer-Lehmann graph isomorphism test. So it's a classical algorithm in graph theory that tries to determine if two graphs are structurally similar, if there is an age-preserving bijection between them, called isomorphism. And the way that it works, it's iterative color refinement technique. So it starts with a graph where the nodes are labeled in the same way. So when I say color, I mean discrete label. And then I apply an injective function. You can think of it as a kind of hashing that changes the color of the nodes. And here you can see that initially we have two types of neighborhoods. So we have a blue node with two blue neighbors and a blue node with three blue neighbors. They will be colored differently in green and yellow. We can apply this procedure again. Now we have three kinds of nodes, and at some point the color will stop changing. So at this point we'll output a histogram of colors. And if I give you another graph and I do the same process for this graph and I get a different histogram, I can guarantee that the graphs are not isomorphic. But if I get the same output, I actually don't know for sure. It's a necessary but insufficient condition. And you can find examples of not isomorphic graphs that would be not distinguishable by this coloring procedure. And you can also see why, because if you look at every node, what it sees essentially is a kind of rooted tree or a star shaped graph around every node. And in these graphs, for example, these will be completely indistinguishable. So what is commonly done is, as I mentioned already, using positional encoding that somehow pre-colors the nodes. And you can see that with the use of positional encoding, we can easily distinguish between these differently structured graphs. And this increases the expressive power of graph neural networks. And there have been multiple ways of doing positional encoding. You can, in the simplest case, use even random features. You can use, for example, the eigenvectors of the graph Laplacian operator. You can count substructures such as cycles or paths or cliques, or even use aggregations of bags of subgraphs. But I think we need to be honest, we have no idea what is the right way of choosing the positional encoding. So we want to do something that is more principled and more formal. And finally, another thing that we see often in graph neural networks is this phenomenon of over-squashing and bottlenecks. And it has to do with the fact that in graph neural networks, the graph is both part of the input and the computational structure. So we basically propagate information on the graph. And if we are unlucky in the sense that the graph is structured such that its volume grows exponentially, so we have a lot of nodes, that if we go 1 hop or 2 hop or 3 hop, so the volume grows too fast with the radius. And we also, our problem depends on long distance information. So I need to propagate information from distant nodes, and we have too many of these. We get the phenomenon of over squashing, that I need to squeeze a lot of information into a single feature vector. And empirically, it was shown that graph rewiring, basically changing the graph on which to propagate information, helps with the phenomenon of over squashing and bottleneck. And again, multiple methods have been proposed, but we don't have a clear recipe how to rewire the graph. So we would like to give a principled view on this problem as well. So this is what I will try to present today in the time that I have. So some continuous model for graphs, a principled view on positional encoding, and if time remains, also how to do principled way graph rewiring. So let me start with a continuous model, and this is our recent paper from ICML on neural diffusion on graphs. So diffusion processes in general are pretty old, so they have been studied in various fields of science for centuries. Probably one of the first or the early principled studies of diffusion, of thermal diffusion, was done by Isaac Newton. Sir Isaac Newton, he published in 1701 anonymously a paper in the Proceedings of the Royal Society about measuring temperature, and that's where he described what nowadays is called the Newton law of cooling, stating that the temperature of hot body loses in a given time is proportional to the temperature difference between the object and the environment. So it's a kind of global behavior, and well, it was a kind of hodgepodge of terminology because he used the term calor, which in Latin literally means heat, and now we understand by heat something completely different. So the right term would be temperature, that was yet to be invented. So the next step was done by Fourier, that derived what today is called the Fourier heat conduction law, that already formulates it in terms of differential calculus, stating that the heat flux resulting from thermal conduction is proportional to the magnitude of the temperature gradient and opposite to it in sign. So it's already some local differential rule, and the final part of it is due to Fick, who studied chemical diffusion, and he said that temperature change in time equals to heat flux through volume. So it's a kind of conservation law, and now putting all these things together, we can write what is called the diffusion equation. So if you think of different temperature in some domain, basically the temperature gradient creates the flow of heat, the heat flux, that is inversely proportional to the negative gradient of the temperature. And the Fick's law is a conservation condition. It tells us that no heat is created or disappears, so the change in the temperature is only due to the heat flux. So basically together this gives us the diffusion equation. The left-hand side is the change in time, the right-hand side governs the spatial behavior of the temperature. And in the simplest case, when the property of the medium are such that the heat flows equally in the same, at every point in the same direction, we have constant diffusivity. This is what is called homogeneous and isotopic diffusion. And we can interpret it either as the gradient flow of what is called the Dirichlet energy, right? So it's kind of minimization process of this energy, or we can even write it in closed form solution as convolution with the Gaussian filter in the Euclidean case. We can also consider more interesting forms of diffusion where the diffusivity is position dependent. So this is called non-homogeneous diffusion, or is also direction dependent. This is called an isotopic diffusion. And the non-homogeneous case attracted a lot of attention in image processing, where it was shown that you can apply this diffusion process to an image, and if you choose the diffusivity function in such a way that it discourages diffusion across discontinuities in an image, basically you don't diffuse across edges, you get nice image denoising that doesn't destroy the structure of the image. So that was the seminal work of Pietro Perrone and Jitendra Malik from the 90s, and it had a lot of follow-up in the image processing community. And here you can see an example the portrait of Sir Isaac diffused with the standard diffusion, convolution with the Gaussian, and this nonlinear diffusion that removes the noise but nicely preserves the discontinuous structures. So we can apply the same ideas to graphs. Basically, we have immediate formal analogy between all the operators that we defined in the plane on the graph. So we can define the gradient as the difference between the features in a pair of nodes connected by an edge. Divergence will be the sum of features of the neighbors of a node, and these two operators, same way as in the continuous case, are formally adjoint. And we can define the Laplacian operator, that is the divergence of the gradient, or we can think of it as the difference between the features in a node and its neighborhood. And this is how the diffusion equation looks on graphs. So it has exactly the same structure as before. This is our discrete graph gradient. This is the diffusivity function. So we'll see that immediately that we can interpret it as attention in graph attention networks. And we will assume that it's normalized. And this is our divergence. So it has exactly the same structure of divergence of a gradient scaled by something. So in order to solve this equation, we need to use numerical solvers. Usually it doesn't have closed form solution. So standard way would be to discretize it. And we can discretize it with explicit or forward Euler discretization, basically taking forward differences instead of the continuous temporal derivatives. And this is how it looks like. So I can rewrite it in matrix vector form. And this is how it looks like. So one thing that you notice is that the matrix here that represents how the next iteration looks like has exactly the same graph adjacency structure. Usually it is sparse. Another thing that we can show, this is standard exercise in partial differential equations, that this scheme is stable if tau is sufficiently small. So explicit schemes are usually stable only with small step size. We can also see that it is equivalent to graph attention network if we assume no nonlinearity and a step size of 1. So in this case, the diffusivity is exactly the attention function of the gut neural network. And of course, we can use other more interesting schemes. So here's a semi-implicit or backward Euler discretization, where we take a backward time derivative. And here we get a system of equations where we need, in order to compute the next iterate, we need to solve a linear system or invert this matrix B. And now this matrix B will not necessarily be sparse. Actually, in most cases, it will be dense. And this is analogous to a multi-hop filter. Basically, I'm not looking only at my neighbor nodes. I need to look at information from multiple nodes. The advantage of this scheme, of course, that it's unconditionally stable. So I can take tau as large as I want. And this is just one example. There is a plethora of literature in numerical analysis of different explicit or implicit schemes that use multiple steps, adaptive step size, and so on and so forth. So we can really leverage a lot of this theory and implement a learnable diffusion process that we call graph neural diffusion or GRAND. So in this case, we solve this diffusion equation where the diffusivity function is parametric and the parameters are learned for a specific task. What is interesting here is that we specifically choose to work with time-independent diffusivity function. So in the language of neural networks, it means that we have parameters that are shared across layers. Every layer has the same set of parameters. And this dramatically reduces the numbers of parameters. As I will see in a few seconds, it's actually a big advantage. So what do we gain from this? You can see that this is just maybe some vain exercise. First of all, we get a new perspective on old problems, like the problem of oversmoothing in graph neural networks, the problem of bottlenecks. It also yields new architectures. So first we can formalize some existing architectures as a discretized graph diffusion equation, but we can also leverage more efficient solvers such as multi-step adaptive or multi-grid solvers that do not have immediate analogy in the graph neural network architecture world. So I think this is just the beginning of a new generation of architectures. We can also get some theoretical guarantees about stability convergence, so something that has been, I would say, quite direly lacking in GraphML literature, and also deeper links to other fields that are less known in machine learning, such as differential geometry and algebraic topology. So many of these things are related to these topics, and I'm not sure I will have sufficient time to talk about it. So here's one example. One of the difficulties, for example, that are well known for graph neural networks, that it's difficult to create a deep graph neural network architecture. We see different phenomena such as oversmoothing. So when you add more layers, then the performance degrades. So in this case, we don't have the depth in the ordinary sense of the number of layers in deep learning. Here, the analogy of depth is the diffusion time. And if you use simple explicit scheme with fixed iteration step, we can think of the number of layers, right, as the number of iterations. Basically, we divide the diffusion time by the time step. In adaptive schemes, we can have bigger steps, meaning that we have less layers, but the layers do something else. And in implicit schemes, we can trade off depth versus width, basically the number of hops that we take in the graph. And well, these are some benchmarks on standard data sets that are used in the community. So the method performs better or on par with other methods, but maybe have a look at the difference in the number of parameters. So the standard GATT architecture uses more than 1.5 million parameters. Here we use less than 100,000 parameters. That's exactly because of these shared parameters that I mentioned in the beginning. Now, what is still missing here is that we look so far at the discretization of the time, which is somehow is pretty easy, but we didn't look at the spatial domain, right? And if we take a step back and think of diffusion in the plane, the way we discretize it is really up to us, right? So if you take a grid, for example, and you have isotopic diffusion, so we have the Laplacian operator, you can discretize it any way you want, right? So any of these numerical stencils will work, right? Or any combination of them because of linearity. So we really have a lot of flexibility in how we discretize continuous differential operators. Can we do something like this on graphs? And this is the idea of graphical Beltrami flow. So this was our paper we presented last week at NeurIPS. And the idea is to look at this anisotropic diffusion in a different way. So before that, we had a nonlinear diffusion where we have the diffusivity function that adaptively told us to run the diffusion faster or slower, or maybe stop it completely. An alternative way is to look at the image as an embedded surface, and we have a non-Euclidean version of diffusion on this surface where we replace the Laplacian with what is called the Laplace-Beltrami operator. So it's a non-Euclidean differential operator. So more formally, we consider the image as an embedded two-dimensional manifold. So in case of, for example, an RGB image, you can think of it as a two-dimensional surface in R5. So we have the geometric coordinates, right, and or the positional coordinates and the feature coordinates. So the positional coordinates will be, in this case, U1 and U2, right, the X and Y coordinates, and the feature coordinates will be R, G, and B channels of the image. Okay, and we can define, thinking of it as a manifold, we can define a metric on this manifold by the pullback from the embedding. And the Beltrami flow is a gradient flow of a special energy that is called the Polyakov functional. So it's an harmonic energy of the embedding, and it's very popular in some fields of physics, such as string theory, where it can also be explained. Basically, it's a geometric theory that gives rise to certain properties of particles. And this is how it looks like. So we can also think of it as a generalization of the Perona and Malik scheme, where the diffusivity function comes from the Riemannian metric of this manifold. So we can apply exactly the same idea to graphs, and we can formulate the Beltrami analogy of Beltrami flow on graph, where now we have a pair of coordinates for each node. So we have the positional coordinate and the feature coordinate, and we evolve both. So we have evolved both. We do the diffusion of the features of the graph and the diffusion of the graph itself. And now you see that we don't really have a graph. The graph is replaced by the positional coordinates, so we can rewire it as we like. So if the nodes, the positional coordinates change and they move, we can adapt the graph on the fly. And probably it's one picture is worth 1,000 words. So here you can see the standard Cora graph. So this is a citation network. So here the nodes represent papers. The colors represent well, some low-dimensional embedding of their features, and the positions of the nodes represent the positional embedding, again some low-dimensional projection. So you can see that as we evolve, as we run this diffusion equation, both the features diffuse as well as the positional coordinates. And the graph is rewired on the fly. So we change the graph as the positional coordinates change. And you can see that many graph neural network architectures can be interpreted as particular instances of this architecture. So it is indeed very general and very broad. And of course, it produces better results. But I think what is probably most interesting is that it gets this interesting link to differential geometry that is a little bit exotic and probably less known in machine learning, even though judging by this year's new RIPs, there are many more papers that try to introduce geometric models in ML. So I will finish. I will not. I don't have time to go into too much details about this other paper, but basically this idea that you do something on a domain that moves under your feet in some sense might be very exotic in machine learning, but it's very common and very standard in differential geometry. And one particular celebrated result or set of tools that are used in differential geometry is what is called the Rishi Flow. So the Rishi Flow is a kind of evolution of the metric of the manifold. So it's a partial differential equation that structurally looks like the diffusion equation. So we have the temporal derivative of the Riemannian metric on the left side, and we have the Ricci curvature. Basically, it's a second order derivative, second order operator, if you think of it, of the manifold. And basically, by making this evolution, we change the manifold itself. So this is how a manifold that looks like this kind of a dumbbell would evolve under the Ricci flow. So here the colors represent positive and negative curvature. And the Ricci curvature was named after Gregorio Ricci Curbastro, an early Italian differential geometer. The concept itself was introduced by Richard Hamilton as a way towards proving the Poincare conjecture, and it was used in a successful way by Grigori Perelman about 20 years ago in what science declared as the breakthrough of the year, the proof of the Poincare conjecture. So this technique, or more specifically Ricci flow with surgery, was used to prove this 100+ years old result in differential geometry. So what does it have to do at all with graph neural networks? And again, let me mention the oversquashing phenomenon, which is the failure of message passing to efficiently propagate information in a graph due to some structural characteristics that are called the bottleneck. And as I mentioned, it occurs in problems where we have long distance dependencies that require information from nodes that are k hops away. And a good example is application of graph neural networks in chemistry, where you have a molecule that maybe the properties of the molecule will depend on atoms on two different sides of this graph. So we need to propagate information from these nodes, from these atoms on the graph, and it might be difficult. So we also see it acutely in graphs with exponential volume growth, right, where you have too many neighbors, and it tends to deteriorate with the depth of graph neural networks. And it is empirically alleviated by graph rewiring. So what we try to do in this paper is formally define oversquashing, relate oversquashing to structural characteristics of the graph that are manifested geometrically through negative curvature. So we need some definition of what is meant by curvature of a graph, and then an algorithm that rewires the graph in a way that is similar to Ricci flow, that makes just a few surgeries to alleviate these bottlenecks. So I think I probably have something like 5 minutes, so let me just briefly overview these results. So the way that we think of oversquashing is a kind of sensitivity analysis. So if we think of a message passing type graph neural network, basically at some layer L+1, we have the dependency on the neighbor nodes, the features produced by the previous layer. So if we apply it multiple times, we can trace back the influence of the input, right? So what we want to say is how sensitive is the feature produced by some layer of this graph neural network at node I to some source node that is geodesically r distant from this node. So I have a node that is a few hops away. I change the input feature vector. I want to see how the output of the graph neural network at the distant node is influenced by this change. So it's standard sensitivity analysis. It is given by the Jacobian of this equation. And you can see that we can write a bound. It depends on the properties of the activation functions, but also on the adjacency matrix of the graph. So the graph structure enters here in some way that it is not very explicit, right? So it's not very clear. Basically, it's some power of the matrix, right? So basically, it hides some structural properties of the graph here. So a pathological example is a binary tree, right? So in a tree, the dependency decays very fast exponentially with how deep we go in the tree. So this is probably the worst example that can happen. Now, a standard, basically what we expect to see here is that something that looks like a grid will behave nicer than something that looks like a tree. And the standard way in differential geometry to distinguish between things that look like a tree, right, or a discrete or continuous analogy of it, something that looks like a plane, is curvature. So curvature can be defined in many ways, but one way to think of it is, if I take two nearby points and I send geodesics at the same velocity from them, what happens to them? Whether they will converge, and in this case we locally look like a sphere, they remain parallel, in this case we're flat, we locally look like a plane, or if they diverge. So in this case we have hyperbolic geometry. So this can be measured by curvature, and in the first case we have positive curvature, in the second case we have zero curvature or flat curvature, and in the second case we have negative curvature. So this is something that looks like a saddle surface. So this analogy of geodesic dispersion can be also applied to graphs. And in a graph, if we take two nearby nodes, right, that are connected by an edge, if we see that basically edges that are shot from these 2 points, 2 nodes, tend to form triangles, we have something that looks like a sphere. So a clique is an analogy of spherical geometry in the discrete case. If they remain parallel, right, they form rectangles, so we get something that looks like a grid. And if they don't form anything, right, if they become further away, then we have something that looks like a tree. This will be the discrete analogy of a negatively curved surface. So we can define, well, let me not go into the details, an analogy of Ricci curvature for every edge of the graph that is computed locally, combinatorially, just by counting the number of these low-level structures. So there are multiple definitions of something similar to the Ricci curvature on graphs, so particular to constructions due to Olivier and Foreman. So we have our own construction that behaves similarly to the continuous case. So for example, cliques will be positively curved, grids will have zero curvature, and trees have negative curvature. And we can also relate it to the well-studied curvature, such as the Olivier curvature that is related to optimal transport. So our curvature is a lower bound on it. And we can show, for example, that when our graph is positively curved, then the volume growth is polynomial, as again we expect in the continuous case. And the main result is, again, let me abstract out the details, is that we can relate over squashing to curvature. So what we show is that if the graph is negatively curved, then basically we have an upper bound on these Jacobian. So in other words, we have limited sensitivity of the graph neural network, or in other words, over squashing can be attributed to the negatively curved edges. So that's the main result of the paper, and we show a process that is similar to backward Rishi Flow that surgically removes or adds edges in the graph to alleviate these negatively curved edges. So we also show that we can relate it to spectral properties of the graph, and in particular important property that is called the Chigger constant. And we also show that diffusion-based approaches for graph rewiring do not necessarily improve graph bottlenecks. And this is particularly acute in the heterophilic case, where the neighbors of a node are not necessarily similar to the node itself. Basically, diffusion-based approaches tend to connect, tend to create new connections in part of the graph that is already strongly connected. And in case of heterophily, this can create disasters. And in fact, this is confirmed experimentally, that in the case of low homophily, these methods do not perform well, as opposed to this surgical Ricci-inspired method. And also, we touch much less the graph, exactly because of this property. So this is an example of a graph that we try to rewire. So diffusion-based rewiring changes it dramatically, whereas in our case, the change is only negligible. So let me conclude it here. So I hope to have shown maybe a little bit briefly and a little bit rationally some links between graph neural networks, differential geometry, and partial differential equations. So it's really a new set of powerful tools that previously have not been well known in this field to study problems in GraphML from different perspectives. It also allows, in particular in these works, to take principled position on some architectural choices that so far have been mostly empirical, such as positional encoding, graph rewiring, and I think it's just the beginning. There might be many interesting follow-up works, and there are still many interesting open questions in this field, but it is probably one of the first mathematical passes towards better understanding what these methods do. So I will stop here. Thank you very much for your attention.
Thank you, Professor Bronstein. So I open the floor for questions. So if you have any questions, please write them down in the QA panel in Zoom, and I will relay it to Professor Bronstein. And the panelists, if you have any question, please unmute yourself and ask.
Hello. Yeah, so thanks. This is a fascinating talk. Yeah. So I have a small question, is that when you are in order to try squashing, you are doing the graph rewiring algorithm. You are doing some sort of graph rewiring. So and which also takes care of long range relationships, which you are telling that it can also take care of. But won't this graph rewiring also destroy some of the relationships, existing relationships, and how would that effect be?
Yeah, it's a very good question. So and again, I alluded to it, but maybe I should state it again. So one of the difficulties or subtleties in graph neural networks that a graph is both a computational graph and the input graph. So the graph contains both information about your input data. It's part of the input data together with the node or edge features, as well as it is used as a mechanism to exchange information. Now, what was shown in several works that you can depart safely from this graph to do exchange of information. To which extent it's not clear. So that's why graph rewiring, basically we try to change this graph as minimally as possible. But what probably should be done really and in a better way, you should probably start with the diffusion without touching the graph, and then change the graph somehow down the road. So basically you can think of two coupled diffusion equations, right? Or two coupled processes, one diffusion on a given domain, another one the diffusion of the domain itself, like in the Rishi Flow, and some way of coupling these two differential equations. And they can evolve at different speeds. So the diffusion can happen at faster speed, whereas the evolution of the domain, the diffusion of the graph itself, can happen at a slower speed, and basically the relative speed can be learned and dependent on the application.
Oh, okay. Okay, great. Thank you. Yeah, I understand. Yeah.
So we have a question from the audience as well. So when a graph is rewired based on curvature, what happens to the graph in terms of the edge connections? Does information stored in the graph change?
Right, it's a good question. So, so far we didn't consider, so I think two caveats. So this is probably, I wouldn't take this work as a practical advice. I think it's more basically giving a new view of a problem. So I think this kind of rewiring is not necessarily the right thing to do. So we consider the graph where that is unweighted. So we didn't consider weights. Weights are easy to incorporate. Edge features are less easy. And we also, the definition of the curvature doesn't take into account the features. So basically, we can link it to the previous version, the previous talk about Beltrami flow, where we consider a joint embedding of the graph in positional and feature space, and we can easily define a curvature that depends on both. So in my opinion, we must take three things into account when designing efficient graph neural networks. one is the data, basically the features. The second is the graph, and the third is the task. Because depending on the task, we might get, we might want to use a different graph, right? So one task, for example, might depend on the local information. So in this case, we don't really care about these bottlenecks and over squashing. If on the other hand, we have a task that depends on long distance relations, and it can be a task on the same data set, then maybe we'll need to do something to the graph. So I think it's a kind of elusive answer where it depends, right? So it depends on what you're trying to do.
Okay, there is another question. So what happens when nodes and edges get added to the graph? So if the graph is changing, I mean, new nodes and edges are getting added, so how do you deal with that?
Yeah, well, so it's a good question. So I'm not sure that I completely understand the questions. Basically, it can be answered in different ways, but one of the differences, let's say, in the GraphML applications is the difference between inductive and transductive settings. So in transductive setting, you know the graph, and maybe you don't know the labels of some of the nodes, and you try to get the labels, but you have access to always to the structure of the graph. In the inductive setting, which is probably more difficult and more practical, imagine that you have a social network where a new user comes, right? And this new user maybe creates new connections, but you want to make predictions to this new user that has never been seen before in the graph. So the graph itself evolves. And in this case, there are many other architectures. We also worked on this. For example, we had a paper last year where we consider also the temporal aspect. So we consider dynamic graphs that are given as a stream of events that add or remove nodes or edges. It is interesting actually how this physical time can be related to the pseudo time of the diffusion. So we have some kind of dynamically changing domain and also some dynamic process that happens on this domain, right? The information propagation. So there might be some interesting links to optimal control theory. So I've seen a few papers that try to look at graph neural networks from that perspective.
Okay, maybe one last question. So do you consider the graph here to be undirected or directed?
So it doesn't really matter. It can be directed or undirected. So for the diffusion equation, yeah, usually, for example, even the attention function is asymmetric. So basically, the matrices in the equations are not symmetric. Yeah. So.
Yeah, so like for this over smoothing problem, so you can't actually deploy deep graph convolution networks because it smooths out. So there have been some attempts like you kind of use some residual connection or skip connection to kind of keep the information intact or like add more layers. So does it connect anyway to your work as well?
Yeah, so well, it's an interesting question. So basically, there are theoretical results and there are practical results, right? So in practice, you don't really look at the limit, so you stop the diffusion at some point. In principle, this kind of diffusion, in the limit you get the enharmonic solution. So basically, it's a vector in enharmonic space that it's either constant or maybe in some other cases it's not constant. So you really do over smoothing. There are other types of diffusion that do not necessarily lead to this kind of solution. The harmonic space is more interesting, and this is what we are trying to do. So when I alluded to results in algebraic topology, so there is an entire mechanism that is called sheaves, where you can have a more interesting diffusion that doesn't necessarily over smooth. Now, when you allow for graph rewiring, everything changes, and I have not seen really any analysis because basically the diffusion analysis assumes that the domain is fixed. When the domain changes, then it might look differently. Also, the expressive power of such graph neural networks, where the graph changes on the fly, is probably stronger than the Weisfeld-Lehmann algorithm. But again, this is an open question. I haven't seen any theoretical analysis yet.
Okay, so I guess we have one last question from Professor Dasgupta. Please go ahead.
Thank you. So perhaps a simple question. So I just wanted to get some physical intuition behind this Ricky flow, either the Ricky flow itself or what exactly is happening to the graph properties when you are doing this rewiring. Is it that the graph is becoming more expander-like, or is it that you're isolating the communities? I mean, is it possible to understand it in any sort of physical way?
Yeah, so probably the Rishi flow is not a completely fair way of thinking of it. It's actually a backward Rishi flow, or it's analogous to a backward Rishi flow. So Rishi flow, if you apply it to a graph, then it will do some kind of clustering. So it will disconnect communities, right? So if you start with this dumbbell, then the dumbbell will sharpen, and basically its topology will become two distinct spheres. So it will create a thin neck, and then it will disconnect. If you run the Rishi flow backwards, then it will homogenize the curvature, and everything will become looking like a sphere, and it will have a constant curvature. So this is what happens in our case. So we try to somehow make the curvature more uniform on the graph. So we don't want these a few edges where we have negative curvature.
Sorry,
so it becomes more constant.
Thank you.
So let's thank Professor Bronstein once more. And we move on to our next talk. So our next speaker is Professor Irina Gurevich. Hi. So let me quickly introduce her. She is a professor of computer science and director of Ubiquitous Knowledge Processing Lab at Technical University of Darmstadt in Germany. She joined TU Darmstadt in 2005. Her main research focus